This is the answer video for the soda factory. How are you? I hope you're doing well. My name is Dudo. Let's look at what situation we have here. We have a vessel with height h and a cross-sectional area A. And this vessel contains water up to half height. Above the water there is pure CO2 gas present that absorbs into the water. The pressure of the gas is kept constant by adding CO2. The water may be considered to be ideally mixed, while the interfacial area remains flat. The water is continuously refreshed with a flow of carbon dioxide free water at a volumetric flow rate phi v. So this is H2O with C in is 0 and the volumetric flow rate phi v, which we also have going out, and we have H2O with the concentration C out, going out. Question 431. Derive an expression for the overall mass transfer coefficient as seen from the liquid capital KL. At first, this might not seem clear how to go about this. However, I hope you can see that if you would take the CO2 mass balance and fill in all terms, capital KL will show up. This gives the opportunity to isolate this term, leading to the expression that is asked for. Let's do this. The CO2 mass balance over the liquid phase in steady state looks like this. 0 is in minus out. In, the inflow of mass, we can write as the volumetric flow rate phi v times the concentration that comes in. The outflow of mass we can write with the same volumetric flow rate times C out, the concentration that comes out. However, we also have mass transfer due to a concentration difference. This is at the interface. Let's write this as phi m prime prime times the cross-sectional area A. Now, C in is 0 because there's no carbon dioxide in the water that comes in. Because the water is ideally mixed, C out is equal to the concentration within our control volume, which is the liquid phase. Okay, so now let's rearrange and isolate phi m double prime. Note that this C is the concentration of the liquid phase. Okay, now this phi m prime prime we can also write as capital KL times the driving force delta C. This driving force from the perspective of the liquid is given by Cg divided by m minus Cl. Now we have two expressions for phi m double prime. This one and this one. And so they must be equal to each other. Now we can isolate KL. Now the last step we can do is multiply denominator and numerator by m. And this is our final answer for capital KL. Question 432. Derive an expression for the overall mass transfer coefficient as seen from the perspective of the gas, capital Kg. Okay, so remember from the previous question that we can write phi m double prime as KL, capital KL, times Cg divided by m minus Cl. We can rewrite this by taking out 1 over m. But we can also write phi m double prime as seen from the gas phase with the overall mass transfer coefficient as seen from the gas phase. So this is capital Kg times Cg minus mCl. This time we have no term multiplying Cg. What you can see immediately is that if we divide by Cg minus m times Cl on both sides of this equation, we see that capital Kg is capital KL over m. And because we have capital KL from the previous question, this reads as follows: phi Cl divided by Cg minus mCl times A. So this is our final answer for question 432. Question 433. Derive an expression for the partial mass transfer coefficient small kl. Let's write down the sum of partial resistances. Total resistance 1 over capital KL is equal to 1 over small kl plus 1 over m small kg. Now, this is the overall mass transfer coefficient as seen from the liquid. So this is also the total resistance and the partial resistances as seen from the liquid phase. From the previous question, we know that KL, capital KL, is equal to m times capital Kg. Now, to see how I got this expression, this expression you can just gamble with it, so to say, and then check it. So let's check it. When small kg is infinite, then the second term it becomes 0. And then what we have is that 1 over capital KL is equal to 1 over small kl, or capital KL is equal to small kl. And this is what you would expect. Similarly, if for this first term we would take small kl is infinite, then this first term is 0. And what we then would have is that the second term, 1 over m times small kg, is equal to 1 over capital KL, or 1 over m times capital Kg. And then capital Kg is equal to small kg. And that is, again, what you would expect. So this expression must be right. In this case, because we have pure CO2 gas above the water, there is no transfer of CO2 within this layer, within this phase. So there's no resistance here. What you could also say is that the small kg is infinite. So in this case we have the first case I talked about, and this leads to capital KL is equal to small kl, and vice versa. So small kl, well, we already had the expression for capital KL, so small kl is also m times 5v times cl divided by cg minus mcl times a. So we have our final answer. That was all for the answers of this exercise. What did you learn? What was new for you? What do you want to take with you from this exercise? I hope you realize again that the balance over a control volume is the heart of transport phenomena and that it can be used as a tool at any time. Also, I hope you have more confidence in using the partition coefficient and see that with that you can define the driving force and the overall mass transfer coefficient in two equivalent ways. A result of the last is that the total resistance can also be defined in two equivalent ways. Was this explanation helpful to you? Remember that on the forum there is room for your questions. Good luck with the next exercise.